Hello everyone. Today we're going to be talking about different ways for representing atoms. We're going to cover 3 different ways that we can draw or represent them. We're going to use the standard nuclear notation. We're going to use the Bohr-Rutherford diagrams, and we're going to use a Lewis structure. So, in terms of our goals for today, first we're going to learn what an isotope is. And then we're going to learn how to use the standard nuclear notation to do things like tell how many protons, neutrons, or electrons an atom has, and how to do that for different isotopes of the same element. Then we're going to talk about how to draw a Bohr-Rutherford model of an individual atom. You will oftentimes hear these also referred to as planetary models. And then lastly, we're going to talk about how you can draw a Lewis structure of an individual atom. So before we go any further, I want to take a moment and review our elementary particles, because fundamentally when we are drawing atoms, what we're actually doing is we are representing how many protons, neutrons, and electrons they have and where they are in the atom. So a reminder, protons and neutrons we are going to find in the nucleus. Electrons are in the electron cloud. And remember that these drawings are not necessarily going to be accurate to what an actual atom looks like, but the electron cloud can mean different things. In certain of these models, we might not even show the electrons. In certain models, we'll only show particular electrons that we really care about, those valence electrons. And in other models, we're going to represent the electron cloud as instead being these super neat, tidy little electron shells. And remember, those electron shells aren't real. They don't actually exist, but they are a super useful abstraction that helps us to understand atoms and how to understand the kind of chemistry that individual elements can do. So remember that protons are positive, neutrons are neutral, electrons are negative. Protons have a mass of 1 atomic mass unit, neutrons have a mass of 1 atomic mass unit, and the mass of an electron is so small that you can basically ignore it. The new thing on this table that you might not have seen before is you'll notice I have filled out this bar that says formula. So here are a few notes on my abbreviations. That hash symbol, I'm using that as an abbreviation for the word number. So anytime you see that, I just mean the number of something. P plus stands for protons. N and then a 0 as that superscript stands for neutrons, and E with a negative stands for electrons. Makes sense because protons are positive, neutrons are neutral, they have a charge of 0, and electrons are negative. So our formula here is that the number of protons that an atom has is equal to its atomic number. So for example, if I look at my periodic table and I find hydrogen on there, hydrogen is element number 1, right? Its atomic number is 1, so it has 1 proton. Simple. So the number of protons is the atomic number. So that's going to be a whole number. It'll be somewhere between 1 and 118. The number of neutrons is a little bit trickier to calculate. To find the number of neutrons, you take the atomic mass, you round it to the nearest whole number, and then you subtract the number of protons. So the number of neutrons is the atomic mass rounded to the nearest whole number minus the number of protons. For our electrons, typically speaking, if we have a neutral atom, the number of electrons is going to be exactly the same as the number of protons. Right now, we're just talking about neutral atoms, so this is going to be super easy. The number of electrons is equal to the number of protons. Easy peasy. However, pretty soon, we are going to start seeing situations where we have atoms that have gained or lost electrons. If that's the case, if you have what's called an ion, I-O-N, an ion is a charged atom that has gained or lost electrons. And in that case, you could calculate the number of electrons by saying it's the number of protons minus the charge. If right now you're like, what, charge? I don't know anything about that. That's okay, we haven't covered it yet. For now, if I say the word atom, you can assume that the number of electrons is the same as the number of protons. Simple. So that's our review of the elementary particles. If you do not already have this on the back of your periodic table, please take a moment and copy this table onto the back of your periodic table so that you have a quick and easy reference always available to you. All right, the next thing I want to talk about today is the concept of isotopes. So you'll remember one of the things we've said about neutrons is that sometimes atoms will just have an extra neutron, or maybe they'll have one fewer neutron than typical. Because neutrons don't have a charge, they don't really do much to an atom besides increase its mass, or decrease it if there's fewer. So having neutrons just determines how heavy an atom is. On your periodic table, you might have noticed that the mass numbers are almost always decimals, right? Like the mass on the periodic table for my hydrogen atom isn't just 1, it's 1.008. And so where did that 0.008 come from if, one proton is 1 atomic mass unit and 1 neutron is 1 atomic mass unit? How did I end up with this decimal number? And the answer is it's because that mass number is the average mass of a hydrogen atom. Now, most hydrogen atoms in the universe have 1 proton. So here is an image of a hydrogen atom with 1 proton. Every once in a while, you will come across a hydrogen atom with a proton and a neutron. So that hydrogen atom would have a mass of 2. That's very rare, but it does happen. Sometimes, even rarer, you'll come across hydrogen atoms that have 1 proton. It has to have 1 proton, that's what makes it hydrogen, and 2 neutrons, which would mean it would have an atomic mass of 3. Those 3 versions of hydrogen with 0 neutrons, with 1 neutron, and with 2 neutrons, we call isotopes of hydrogen. All of them are hydrogen. Each of those is a hydrogen atom. The only difference between them is that some of them are heavier than others. So deuterium or tritium is much heavier than ordinary hydrogen would be. So my point here is that you can have a different number of neutrons. This matters a lot because we have different isotopes. And so an individual atom might be of any particular isotope. And that means that an individual atom could have a different mass from another atom of the same element. For example, carbon comes in 3 typical isotopes. There's what we call carbon-12, which is carbon that has a mass of 12, carbon-13, which is carbon that has a mass of 13, and carbon-14, which is carbon that has a mass of 14. So all of those are isotopes of carbon. And here you can see them written out. Now, carbon is element number 6 on the periodic table. It has 6 protons. So you can see in this is what we call standard notation. It's a way of representing an atom, and it's very important if you want to talk about different isotopes. You can see we have the element symbol. So the C there stands for carbon. We have the atomic mass. So in the case of this isotope, carbon-12, its mass is 12. In the case of this isotope, carbon-13, its mass is 13. And in the case of this isotope, carbon-14, its mass is 14. And we have the atomic number. Because carbon always has 6 protons, having 6 protons is what makes you carbon. You can see the atomic number for all 3 of these isotopes is the same. It's 6. So what you've just seen is an example of standard notation. It's a way of writing an atom down. So typically in standard notation, there are 3 things to think about. In the center, the big thing, is the elemental symbol. So if this was carbon, you would put a C there. If it was hydrogen, you would have an H there. You would put whatever symbol exists for the atom you are talking about, for the element you're talking about. On top, here where they just put A, you're going to put the mass number. Now, standard nuclear notation typically refers to a particular atom or a particular isotope. So this mass number is going to be a whole number. It's not going to be the decimal number that you see on the periodic table. If you think about elements like lithium, if you look at lithium on your periodic table, you'll see it has a mass of 6.941, What that really means is that most lithium atoms have a mass of 7, 6.9 is almost 7, but every once in a while you have a lithium with a mass of 6. So if I was writing about the isotope called lithium-7, which is to say lithium with a mass of 7, I would write 7 as the mass number. But if I was talking about the isotope lithium-6, lithium with a mass of 6, I would put a 6 there for the mass number. Just like on this previous page, you can see we've got different mass numbers for the different isotopes of carbon, but all of those are whole numbers. Now at the bottom where they've written Z, you would put the atomic number, which is the number of protons. So if I was doing hydrogen, hydrogen is the very first element on the periodic table, its atomic number is 1, it has 1 proton, having 1 proton is what makes it hydrogen. I would put a 1 right here where it says atomic number. So that is the standard nuclear notation for representing an atom. All right, next up we are going to talk about a way of representing atoms called the Bohr-Rutherford diagram, also known as the planetary model of an atom. It's oftentimes called a planetary model because it looks kind of like a solar system, where you've got the sun at the center, that's the nucleus in this example, and then planets orbiting around it. In this case, the planets are the electrons. So let's start with an element like lithium. So lithium is element number 3 on your periodic table. And if you look at lithium on your periodic table, you'll see it has an atomic mass of 6.9. Now, an individual atom cannot have a fraction of a nucleus. You can't have 0.9 neutrons. You can only have a whole number of neutrons or protons or electrons. So I could have a lithium with a mass of 7, or I could have a lithium with a mass of 6. Those would be 2 different isotopes of lithium. So let's assume for the purposes of this that we are talking about lithium-7. So its mass number is 7. Our elemental symbol is Li. Now lithium is the 3rd element on the periodic table, so its atomic number is 3. Now we already know a fair bit about lithium. We know that it has 3 protons because its atomic number is 3. So we've got 3 protons. We know how many neutrons it has because we have the mass number and the atomic number. And the mass is basically all of the protons plus all of the neutrons. So if we have 7 protons plus neutrons, and 3 of them are protons, the rest must be neutrons. So 7 minus 3 tells us that there are 4 neutrons present. So 3 of the mass came from protons, the remaining 4 of the mass came from neutrons. And then when it comes to electrons, we know that if there are 3 positive charges, but this is a neutral atom, there must be the same number of negative charges. So if we've got 3 pluses in 3 protons, we must have 3 negative charges and 3 electrons. So when we're drawing this atom, we're going to be drawing the protons, the neutrons, and the electrons. So protons and neutrons, as you recall, are in the nucleus. So we will start by drawing the nucleus. So one way you'll see people do this is you'll see them draw each and every proton and neutron. So if I'm going to do that, I'll have 7 circles total. So let me draw 7 circles here. 1, 2, 3, 4, 5, 6, 7. And then 3 of them are protons, so I'm going to put a plus in 3 of those. Try to spread them out, don't put them all right next to each other. And that would be my nucleus. So we've got 4 neutrons and 3 protons. You can see I've stuck a plus in the protons to make sure that they're clearly labeled. Now lithium is in the 2nd row of the periodic table. Because it's in the 2nd row, that means that it has 2 electron shells. So I'm going to go ahead and draw those electron shells. This is where we are going to put the electrons. Now, each shell can hold a different number of electrons. That first innermost shell is really small. It can only hold 2 electrons. By the way, you'll notice that the first row of the periodic table only has 2 elements in it. This is why. Hydrogen and helium are those first 2 elements. Those fill up this innermost shell. So shell 1 can hold 2 electrons. This second shell can hold up to 8 electrons. So shell number 2 can hold 8 electrons. So if you look at the second row of the periodic table, you will notice that there are 8 elements in that second row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's 8 elements. It's 8 electrons to fill up that second shell. So for lithium, we have 3 electrons to work with. You always start by filling in the innermost electron shell, which can hold 2 electrons. So I'm going to put 1, 2 electrons in that first innermost shell. Then I'm going to start filling in the next shell. Because this one's full, I've got to move to the next shell out. So I've got 1 electron left, because we've got 3 total. So that 1 electron goes in the outermost shell. So lithium has 3 electrons total, 1, 2, 3, but only 1 valence electron. So 1 valence electron. You'll also note that lithium is in column 1A, that very first column of the periodic table. The column that it's in tells us how many valence electrons it has. So lithium's in the first column, it has 1 valence electron. Now there's another way that you can draw these, and that is sometimes when people draw these, if they've got a bigger atom, drawing all these circles for the protons and neutrons can get really difficult. So one thing that you'll sometimes see people do, and you are welcome to do this, it'll save you a lot of time, is instead of drawing all these circles for the protons and neutrons, we can basically, in the center, just write how many protons and neutrons there are. So you can say like 3p plus, which means 3 protons, and 4 n0, which means 4 neutrons. Stick that in like a little box in the center, and that can represent your nucleus. So you're welcome to do this to represent your nucleus. It'll save you a lot of time. All right, let's look at a larger atom. Let's do sodium next. So sodium, it has the symbol Na. Sodium is element number 11. So its atomic number, and therefore its number of protons, is 11. If you look at its mass on the periodic table, you will see it is 22.990. Again, you can't have a fraction or a decimal number of neutrons. So really, there's multiple different isotopes of sodium. In this case, let's assume we're dealing with the most common isotope, which would be sodium-23. So sodium with a mass of 23. I just rounded that 22.9 to the nearest whole number and got 23. So this tells us that there are 11 protons. There are 23 minus 11 neutrons, so that is 12 neutrons. And then we have 11 positive charges, so we must have 11 negative charges, 11 electrons, to balance out those protons. So in our nucleus, which is the first thing we draw, I'm just going to say, we got 11 protons and we've got 12 neutrons, because I do not have time to draw 23 circles and put 11 pluses in them. So we're just going to do that. And that's going to represent our nucleus. Now, looking at sodium, it is in the 3rd row of the periodic table. So that means it is going to have 1, 2, 3 electron shells, because it is in the 3rd row. We have 11 electrons total to work with. So first shell, that's easy, we've done that before. We're going to go 1, 2. Now, for this second shell, and also for the third shell, I'm actually going to be a little bit picky about how you place your electrons. I want you to imagine a compass rose. So we've basically got north, east, south, and west. The rule is, when you place your electrons, I want you to start by putting an electron into each quadrant until obviously you run out of electrons. Only once you've put an electron in each quadrant can you make pairs. So basically there's only a couple of different zones we're going to stick these electrons in. So we've got 11 electrons total. We've already used 2. That means we're down to 9 electrons. We can only fit 8 of them in this second shell. So let's start placing them. 1, 2, 3, 4. I've stuck an electron in each quadrant. Once I've stuck an electron in each quadrant, I can start making pairs. It turns out electrons love to be in pairs. It makes the atom stable. So I'm going to keep placing them. I've placed 4 in this second shell so far. Second shell can hold up to 8. So 5, 6, 7, 8. Once every electron in that second shell has a partner, it's full. I can't stick any more electrons in that second shell. I have to move to the third shell. So then I've got 1 electron left because I've used 2 here and 8 here, that's 10 total. I've got 1 electron left. So I'll stick that 1 electron in that third shell. Again, sticking to my quadrants. So this is how I would go about drawing an element like sodium. I really am going to be picky about these placements, and the reason why is because it will absolutely significantly help you when you are working with the next way of drawing atoms we're going to talk about, which is Lewis structures. Hi folks, so I had initially planned on covering Lewis structures today, and as I went through this video I realized that honestly it was getting really long and I didn't want to give you too much all at once because I was afraid it might be overwhelming. So we will cover Lewis structures in my next video. Before you move on though, I've got a couple last notes. Please make sure, if you have not done so already, that you have this table copied onto the back of your periodic table. You want this periodic table to sort of serve as a one-stop shop for all of your most important chemistry notes. So this is something that I want you to always have access to. Please copy it down onto the back of your table. The other thing I want you to make sure that you have written down on your table is this standard nuclear notation. So please make sure you have that written down. So here's the back of my table, and you can see I've got my elementary particles table and my standard nuclear notation notes. So that should be there available to you right on the back of your table so you always have it accessible without ever having to go on a search. The last thing that I want to clarify, because I oftentimes get questions about it, is when it comes to the positioning of those electrons in your model, which electrons end up in pairs versus unpaired doesn't matter. So for example, right now on the board, this is a fluorine atom. And this fluorine atom currently has pairs of electrons in the east, north, and west quadrant, and the southern quadrant one is unpaired. However, it is equally fine if there's pairs, northwest and south, and the east one is unpaired. Equally good, totally valid, no issues. It's totally fine if the pairs are in the east, south, and west, and the north one is unpaired. None of that matters. What matters is that outermost shell has 7 valence electrons, 3 of them are in pairs, 1 of them is unpaired. That's what matters for this particular element. So please know that which quadrant ends up unpaired isn't the one that matters in a problem like this. What matters is how many of them are paired and how many of them are unpaired. So please make sure you're particularly vigilant about that when you are drawing your planetary models. You will probably see on the internet and in other places people arranging their electrons in other ways. The next step we're going to move for, Lewis structures, is all about those valence electrons, and I promise you, if you arrange your electrons this way, it will make that next step so much easier. So please do be mindful about putting the electrons into those quadrants. All right, good luck.